When integrating subpanels and lighting control relay panels in a commercial building, there are several key considerations to ensure a safe, efficient, and code-compliant installation. Firstly, proper planning is essential. Begin by thoroughly assessing the building's electrical load requirements, including both present and future needs. This involves calculating the total amperage required for lighting, HVAC systems, equipment, and any other electrical load. The subpanels and lighting control relay panel must be adequately sized to accommodate these loads, with sufficient capacity for future expansion. Secondly, the electrical code compliance is paramount. All work must adhere to the latest edition of the National Electrical Code, or NEC, as well as any applicable state or local codes. In California, pay close attention to California Electrical Code, or SIC, which incorporates the NEC with amendments specific to the state. This includes requirements for wiring methods, overcurrent protection, grounding, and bonding. Thirdly, when physically connecting subpanels side by side, ensure that there is sufficient working space around the panels as required by the NEC. Article 110.26 of the NEC specifies minimum working clearances in front of electrical equipment based on voltage and condition of the installation. This working space must be maintained clear of obstructions to allow for safe access and maintenance. Fourthly, the correct wiring methods are important. Use appropriate conductors and wiring methods for the voltage, amperage, and environment. Conductors must be sized according to NEC Table 310.16, based on their ampacity and temperature rating, taking into account any directing factors for ambient temperature or conduit fill. Use appropriate conduit or cable types for the specific application, such as EMT, or electrical metallic tubing, or MC, or metal clive cable. Fifthly, consider overcurrent protection. Each subpanel must be protected by a main overcurrent device, such as a circuit breaker or fuses, sized to protect the panel's busbars and connected circuits. Branch circuits within the subpanel must also be protected by individual circuit breakers or fuses, sized according to the ampacity of the conductors and the requirements of the connected equipment. Sixthly, grounding and bonding is critical. Proper grounding and bonding are essential for safety and to minimize the risk of electrical shock. Ground all non-current carrying metal parts of the subpanels and lighting control relay panel, and bond them together to create a lower impedance path to ground. Use a grounding electrode system that complies with NEC Article 250, such as a ground rod, ground ring, or connection to the building's metal frame. Seventhly, when integrating the lighting control relay panel, ensure that it is compatible with the lighting system and that it is properly wired and configured. The relay panel should be listed and labeled for its intended use and should be installed according to the manufacturer's instructions. Use appropriate control wiring and communication protocols to interface the relay panel with lighting sensors, switches, and other control devices. Eighthly, labeling and documentation is necessary. Label all circuits and components clearly and accurately to facilitate identification and maintenance. Provide detailed documentation of the electrical system, including panel schedules, wiring diagrams, and equipment specifications. This documentation should be kept in a readily accessible location for future reference. Ninthly, for energy efficiency, implement strategies to minimize energy consumption and reduce operating costs. Use energy-efficient lighting fixtures and controls, such as LED lighting and occupancy sensors. Consider implementing a lighting control system that can automatically adjust lighting levels based on occupancy, daylight availability, and time of day. Tenthly, surge protection is helpful. Install surge protective devices, or SPDs, at the main service entrance and at subpanels to protect against voltage surges and transient overvoltages. SPD can help to prevent damage to sensitive electronic equipment and reduce the risk of electrical fires. 11thly, inspect and test the installation thoroughly. After completing the installation, inspect and test all wiring, connections, and equipment to ensure that they are functioning properly. Use appropriate test instruments, such as a multimeter, to verify voltage, current, and continuity. Perform insulation resistance tests to check for insulation damage or leakage current. 12thly, consider load balancing. Balance the load across the phases of the electrical system to minimize voltage imbalances and reduce neutral current. Unevenly distributed loads can lead to overheating, voltage sags, and other problems. Use a clamp on ammeter to measure the current on each phase and adjust the load distribution as needed. 13thly, for the coordination of overcurrent devices, ensure that the overcurrent devices are coordinated to minimize nuisance tripping and to provide selective fault clearing. This involves selecting circuit breakers or fuses with appropriate time current characteristics so that the device closest to the fault will trip first, while upstream devices remain closed. 14thly, follow safety precautions. Always follow safe work practices when working with electrical equipment. De-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as insulated gloves, safety glasses, and arc-rated clothing. 15thly, regarding arc flash hazard analysis, conduct an arc flash hazard analysis to determine the potential arc flash hazards associated with the electrical equipment. This analysis should identify the incident energy levels and the required PPE for qualified personnel working on or near the equipment. 16thly, maintenance is required. Establish a regular maintenance program to inspect and maintain the electrical system. This program should include periodic inspections of wiring, connections, and equipment, as well as cleaning, tightening, and lubrication as needed. Keep records of all maintenance activities and repairs. 17thly, regarding professional consultation, consult with a qualified electrical engineer or contractor to ensure that the electrical system is properly designed, installed, and maintained. They can provide valuable expertise and guidance on code compliance, safety, and energy efficiency. 18thly, consider the impact of harmonics. Harmonics are distortions of the sinusoidal waveform of alternating current that can be caused by nonlinear loads, such as electronic ballasts, variable frequency drives, and computers. Harmonics can cause overheating, voltage distortion, and equipment malfunction. Consider installing harmonic filters to mitigate the effects of harmonics. 19thly, regarding power quality monitoring, install power quality monitoring equipment to continuously monitor the electrical system for voltage sags, swells, transients, and other power quality problems. This equipment can provide valuable data for troubleshooting and identifying potential problems. 20thly, for future expansion, plan for future expansion of the electrical system. Provide spare capacity in the subpanels and raceways to accommodate future loads. Consider using modular equipment that can be easily expanded or reconfigured as needed. 21st, consider renewable energy sources. If feasible, consider incorporating renewable energy sources such as solar photovoltaic or PV panels into the electrical system. This can help to reduce energy costs and greenhouse gas emissions. 22ndly, for energy storage systems, consider installing an energy storage system, such as batteries, to provide backup power during outages or to store excess energy generated by renewable energy sources. 23rdly, for demand response programs, participate in demand response programs offered by the local utility to reduce energy consumption during peak demand periods. These programs can provide financial incentives for reducing energy use during specific times. 24thly, regarding smart grid technologies, implement smart grid technologies such as smart meters and automated control systems to improve the efficiency and reliability of the electrical system. These technologies can provide real-time data on energy consumption and allow for remote monitoring and control of electrical equipment. 25thly, when integrating subpanels and lighting control relay panels, it's crucial to thoroughly understand the system's design. This involves scrutinizing blueprints, wiring diagrams, and schematics to grasp the intended functionality and interconnections. Pay close attention to the specified voltage levels, current ratings, and control signal types to ensure compatibility and adherence to safety standards. 26thly, proper component selection is paramount. Choose subpanels and lighting control relay panels that are specifically designed for commercial applications and meet or exceed all relevant industry standards. Consider factors such as load capacity, environmental conditions, and ease of maintenance when making your selections. Always opt for reputable brands with a proven track record of reliability and performance. 27thly, the installation process should be meticulous and well documented. Follow the manufacturer's instructions and any applicable codes and regulations. Ensure that all wiring connections are secure and properly labeled. Document the installation process with photographs and detailed notes for future reference and troubleshooting. 28thly, thorough testing and commissioning are essential. Before putting the integrated system into service, perform comprehensive testing to verify its functionality and safety. This should include voltage and current measurements, insulation resistance tests, and functional tests of the lighting control system. Address any issues or discrepancies promptly and retest as needed. 29thly, ongoing monitoring and maintenance are critical for long-term performance and reliability. Implement a regular inspection and maintenance schedule to identify and address potential problems before they escalate. This may include visual inspections, cleaning, and testing of components. Keep detailed records of all maintenance activities. 30thly, in California, it is crucial to stay up to date with the latest regulations and codes pertaining to electrical installations in commercial buildings. The California Electrical Code, SEC, is based on the National Electrical Code, NEC, but includes additional amendments and requirements specific to California. Failure to comply with these regulations can result in fines, delays, and safety hazards. 31stly, emergency preparedness is essential. Develop and implement an emergency plan that addresses potential electrical failures, power outages, and other unforeseen events. This plan should include procedures for safely shutting down equipment, providing backup power, and communicating with building occupants. 32ndly, worker safety should be the top priority. Ensure that all personnel involved in the installation, maintenance, and operation of the integrated system are properly trained and equipped to perform their tasks safely. Provide appropriate personal protective equipment, PPE, and enforce strict adherence to safety protocols. 33rdly, effective communication is key to a successful integration project. Foster open communication among all stakeholders, including electrical engineers, contractors, building owners, and occupants. Regularly share updates, address concerns, and solicit feedback to ensure that the project meets everyone's needs and expectations. 34thly, consider the long-term costs and benefits of the integrated system. While the initial investment may be significant, the long-term energy savings, reduced maintenance costs, and improved reliability can provide a substantial return on investment. Conduct a thorough cost-benefit analysis to justify the project and secure funding. 35thly, when physically connecting subpanels, always maintain proper separation and isolation between circuits of different voltage levels. This is essential to prevent electrical faults and ensure the safety of personnel. Use barriers or partitions to physically separate high voltage and low voltage circuits, and clearly label all wiring and components to indicate their voltage levels. 36thly, carefully consider the grounding and bonding requirements for the integrated system. Proper grounding and bonding are essential for preventing electrical shock hazards and ensuring the proper operation of equipment. Follow the guidelines in the National Electrical Code, NEC, Article 250, and consult with a qualified electrical engineer to design a grounding and bonding system that meets the specific needs of the installation. 37thly, when selecting overcurrent protection devices, ensure that they are properly sized and coordinated to protect the wiring and equipment from overloads and short circuits. Use circuit breakers or fuses with appropriate ampacity and interrupting ratings, and coordinate the devices to minimize nuisance tripping and ensure selective fault clearing. 38thly, when integrating lighting control systems, carefully consider the control strategies and user interface. The control system should be intuitive and easy to use, and it should provide the flexibility to adjust lighting levels and schedules to meet the specific needs of the building occupants. Consider using occupancy sensors, daylight sensors, and time clocks to automate lighting control and reduce energy consumption.